Okay, we're going to do something today that's pretty straightforward. It should be straightforward. So far, I think all the programs we've done have been just using integer variable types and Boolean variable types. I want to go through really quickly, adjust my camera really quickly, the decimal data types in Java, which are the floating point variables, and double precision floating point variables. So to do this, I'm just going to do something really, really simple. It's to take two numbers and divide them by one another. And I've chosen 1 and 17 to be the numbers I test because 1 divided by 17 is actually a really, really long decimal before it repeats. So for the first thing, I've just got a skeleton of some code here to create a scanner and read in some input from the user. So I'm just going to ask the user for a number, enter the first number. I'm going to put that into a variable called number1, and it's going to be a float, so a floating point decimal. And to read a float from the scanner, I have to type scanner next float. Remember, when you use the scanner to read stuff, you have to tell it what kind of data type it is expecting. So when we're reading in ints, it was next int. It is now next float. So what is the next floating point variable that someone types into the scanner? And then we'll do it again for the second number. So enter the first number, enter the second number. I should change that to second, huh? Second number. And then number 2 equals scanner next float. So I've read in two numbers from the console. Let's just run that and make sure that that works. Nothing's going to happen because I don't do anything with, 2, nothing happens. I did that too fast. I typed my 2 before it was done asking me. Enter the first number, 2, enter the second number, 3. Okay, it doesn't do anything. So all I'm going to tell it to do with those two numbers is to take them and divide them by one another. And I'm going to create a new variable. I'm going to call it quotient. That's the word for two things divided by one another. And I'm going to make that also a float, a floating point variable. So the quotient is just equal to number 1 divided by number 2. And then I'm going to print that result. So I'll have a system out print line, the quotient of, and then end my little quotes, plus number 1 divided by, in quotes, clicked outside my window, help, where'd I go? Divided by, I don't know why my scroll, there's no scroll at the bottom of my window, I don't know why. I've got to do it this way. Divided by, there it is, number 2 is, and then my quotient. Okay, so it's a big long print statement. The quotient of number 1 divided by number 2, and then it should give me the answer. And I want to use 1 and 17 again because 1 divided by 17 is a long decimal. And so it gives me an answer of, let me put a line feed in here, so my big long decimal all winds up on one line. We'll put it here after the word is, or before the word is. We'll put our /n there to go to a new line. I just want to make sure you can see it in the little window over there. Enter the first number 1, enter the second number 17. The quotient of 1 divided by 17 is 0.05882353. So how many digits of precision do we get from using a float? We get 1, 2, 3, 4, 5, 6, 7 significant digits, 8 digits beyond the decimal point. Okay. What is the right answer, the correct answer, the actual quotient of 1 divided by 17? I took the liberty of just looking this up on Wolfram Alpha before I pasted the code in. And 1 divided by 17 is 0.05882352941176477, and then it repeats. So it's a repeating decimal with a really long 16 digits before it repeats. So what do we get? 0.058882353, 588235529. So we got it out to the what's that? The 1, 2, 3, 4, 5, 6, 7, 8th or 9th decimal point. That's not too bad. But we can do better than that. Instead of using floating point math to do our division, let's do the same thing again, but using a data type called a double, which is short for double precision floating point. You use twice as many bits to store the number, so it can have twice as much, or roughly twice as much accuracy. So we can't call it quotient. We've already used quotient. We'll just call it double quotient. Okay, so we've got a new variable, double quotient, that is of data type double precision floating point number, or double. And now I'm just going to print out the same thing. I'll have a print statement that says the more precise quotient of number 1 and number 2. Again, I don't know why my scroll isn't showing up here. Of number 1 divided by number 2 is, and then double quotient. Okay, so that will give me my second. And maybe let's make sure we have, yeah, we've got a line feed in there, so we'll have a couple blank lines. Let's put another blank line in there just so our data looks, so our output looks nice. Takes a minute. Enter your first number 1, enter your first number 17. The quotient of 1 divided by 17 is 0.05882353. We did that already. The more precise quotient of 1 divided by 17 is 0.058823529630899943. Notice it hasn't repeated yet. That's interesting. Let me put another after the word is, so we can get that number all in one line. Put another line break in here, /n. I just want to be able to look at that number all at once. 1 divided by 17. 058823529630899943. Let's go back to our right answer, our real number that we looked up. I used Wolfram Alpha to compute this number, so I trust that this is the true repeating decimal. What do we got? 588. Sorry, I don't know why I'm having so much trouble today with my browser. 588235294017647. 0.0588235229, but then 630630899. So more precision, more decimals, but we only really got one decimal place better accuracy than the float. That should worry us a little bit. That when we are using computers to do floating point math, we have to be very careful out beyond the 6th, 7th, 8th decimal point and be on the lookout for floating point errors. Even when we use double precision variables. So this answer has more decimals, but it is not a much better answer. It is only better by 1 decimal place, despite having 1, 2, 3, 4, 5, 6, 6 or 7 more decimal points of precision. We talked about floating point errors last time. We talked about the fact, or last semester, those of you who took the Python class with me, that they arise because representing a decimal in, or representing a decimal in a base 10 system like we use, you've got your tenths place and your hundredths place and your thousandths place and your 10,000ths place. But representing those numbers in the computer, you've got a halves place and a quarters place and an eighths place and a 16th place and a 32nd and 64th and 128th place. And in converting from one of those bases to the other, you lose some information. That conversion from a decimal fraction to a binary fraction is lossy. It loses some information. So as you get further and further downstream from that decimal point, you have to be more and more careful that you're not introducing these little tiny round off errors every time you convert a decimal fraction into a floating point binary fraction and vice versa. Okay, so that's just something, again, to be on the lookout. Where most of you need to be doing calculations that are correct to 1 part in 10 million or 100 million? Maybe not. If you're a scientist, maybe yeah. and you just have to be aware that floating point errors are something that can happen, and you have to be on the lookout for them, and always a little suspicious of the accuracy of these numbers once you get really far down from the decimal point. Just to throw in a really quick personal story, when I was doing my PhD thesis, I can switch to the camera here, I think. When I was doing my PhD thesis, it involved about 6 months of computing stuff on paper, and then about 2 years of writing a computer program to actually compute the thing. And the mathematical expression I was computing was a formula that was, I think it was about 50 pages long when you wrote it out by hand in a notebook. So I had to take that 50-page formula, 50-page mathematical expression, translate it into code, and then do a double integral. Those of you who have been through calculus, multivariable calculus, a double integral of that quantity, and make a graph of the result. And at one point, I got a lovely graph where the points went point, 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 and then one point way up here, and then back to this beautiful curve again. And so what does that mean? Does that mean there's an error in my 50 pages of calculation? No, it means I was subtracting two numbers that were very small, and at one of those points there was a weird floating point error that made one of those points just come out wrong. So I had to go and fiddle with my code to try to eliminate that floating point error and kind of calculate around that one mistake. So if you know those things can happen, you aren't surprised when they do, but it's something to always keep an eye out. Is there any reason, since Java has floats and doubles, for us to ever even use floats at all? The answer is not really, because in this class we're not really going to be concerned about saving precious memory space in our programs. We're not going to have hundreds of variables that we're trying to squeeze into a tiny amount of memory. It's probably not something we have to worry about. The other thing is some mathematical functions, the functions that are built into Java, like taking a number to the power of something or taking the sine or cosine of something, will only accept doubles as their arguments. They won't even accept a float. So if you get something like an illegal type conversion or incompatible types, that may be because you are trying to give a float to a function or a method that's expecting a double. So that's something to keep an eye out for. So can you always use doubles instead of floats? Yeah, you can. You can always use longs instead of ints, I guess, if you want. You should just be aware that what you're doing behind the scenes is doubling the amount of memory you use every time you save a variable. So I'll go ahead and leave that there. We'll do maybe one simple floating point math problem. Last semester we calculated infinite series. We did the harmonic series, and then we did a series that computes pi. Maybe I'll do that in Java really quickly. And another thing I want to do, and maybe I'm not sure if I want to do this week or next week, is look at some math applications that will be of interest to those of you who are taking this because you're studying physics or engineering, need to write programs to mathematically compute stuff. We'll look at doing numerical integration, for example, finding the area underneath of a curve using infinite series, breaking that curve down into little rectangles and adding up the area of those rectangles. So we'll do that in the next couple of weeks probably.